We're going Saturday night.
My mom sent me this last night. It's when I was 7. That was iconic.
I was gonna ask for the left-handed desks were in the auditorium.
I think this is when I was 7 years old. I got a perk because I wanted one.
Prove it. Because I have never seen one.
Dane. Do you want to see the most iconic I've ever been? We just watched, I think it was, we watched Legal Women, and I enjoyed the whole perm scene, so my sister told me to perm.
Oh, that's very funny.
Yeah, it was great. I miss that hair.
If I can help it, never show you the picture.
You got it.
No, but you watch Stranger Things.
Oh, I do those characters should be restraints.
And it's like, I know a guy who had that same haircut.
By the way, concerts, they
I could.
Really good.
They always do an introduction.
Oh, that was a I like
So
this
we were
one.
the only ones that got to hear the Albanian.
That's
That was awesome.
You know, it's like.
I chatted with him briefly on the concert.
Where's Ruby's front one?
Yeah.
I thought the cellist was.
For better or worse.
Oh, yeah. Yeah.
I agree.
This weekend is-
We appreciate you getting dressed up.
Oh, is it? Which piece
I'm
did
not
you
taking
like
that
best?
out.
What? Which piece did you like?
It was too hard to get.
There was the.
I had another
the
minute.
Armenian composer, the Hungarian composer, French.
It wasn't French.
We're gonna wait a couple minutes for stragglers to make their way onto the Zoom or in the room.
I don't know why.
Takes away the noise.
You're training your ear, maybe.
All right, hello everyone, and welcome to our last talk in the Summer Student Talk series. So we've seen a bunch of talks already, and today what we will have is a talk by Catalina Zamora about neutral versus ion line widths in L1544. So take it away, Catalina.
Of doing that, then she will come and tell me how the
One
show.
second, let me go mute. If you're on Zoom, please mute yourself. I'll go confirm this for you.
Now he can come, but he can't sleep over.
Okay.
After 2 years of doing it, he can tell children.
Okay, it's the same crap when you come with you.
Do you know this?
There. I was trying to see if I could recognize me. Okay.
You should be good to go.
Hello, everyone. So for the past 2 weeks, I've been working with Dr. Anna Grishminica, and we've been looking at determining line neutral versus ion line widths in pre-stellar core L1544. There it is, right up there, the Torus molecular cloud. It's so cute. But before I give you an introduction to the project, I want to give you an introduction to myself. So I was born and raised in Ringo's, New Jersey, like a good New Jersey, and there's a picture of me in New York City. And when it came time to go to university, I decided to move all the way across the country to Seattle, Washington, where I attend the University of Washington, and there I am a rising senior in astronomy and physics. There's my favorite picture of Mount Rainier from campus. And some of my interests, I really enjoy reading, especially here in Green Bank, West Virginia, where there is no portable internet. I have read 9 books so far. And I really enjoy playing video games, especially this summer. I've gotten really into Stardew Valley. And if this whole astronomy thing doesn't work out, I'm going to be a very successful virtual farmer. This summer, not only have I gotten the privilege to work with everyone here for the past 10 weeks, but I've also been incredibly fortunate to work with and meet these fantastic people and make some great memories. One of them being our trip to Fayetteville, we got to see the new River Gorge Bridge, and we just explored Elizabeth's hometown. It was just such a fantastic time. So that's a little bit about me. So now I want to give you an introduction to my project. So in the past, it has been theorized that the dense gas tracer, ion N2H+, has narrower line widths than that of the neutral, NH3. But observations show that that is actually not the case. So observations of dense core Barnard 5 and other sources show that that is not the case. Here is the sonic Mach number distribution from Barnard 5. It's about 305 parsecs away from us in the Perseus molecular cloud. This graph comes from Pineda and Schmiedicke 2021. And you can see here that the ion N2H+ has a greater distribution than that of the neutral, here proving that it does have a little bit of a wider line width than that of the neutral. And this summer, I have produced more data that tentatively agrees with this hypothesis, but we will get into that. So, what is L1544? So unlike Barnard 5, which is a system that has a more advanced protostar and a bunch of starless cores, L1544 is a prestellar core, which means that it is gravitationally bound and it is on the verge of forming a protostar. So it's located in the Taurus molecular cloud about 130 parsecs away, which means that it is actually a lot closer to us than Barnard 5 was. This allows us to resolve more of its structure. For this project, I used N2H+ data from GBT's Argus instrument and NH3 data from the VLA and its deconfiguration and GBD single dish data, which so coincidentally happens to be the same configuration that was used for Barnard 5. So to start my project, I needed to determine the line widths, and to do that, I needed to learn spectral cube. Backing up a little bit, I didn't need to just learn how to use spectral cube. I needed to learn what a data cube was. So this project is my first introduction to radio astronomy. And if it weren't for my very helpful friends with their useful metaphors, I would say that I would still have a little bit of a shaky understanding of what a data cube was. So I'm grateful for them. But the spectral cube documentation is actually fantastic. I was able to learn a lot from it, like how to just open a cube or import important information from its header into Jupyter. But I mainly use this package to smooth the data both spectrally and spatially. So the spectral resolution of the N2H+ data is actually a lot higher than that of the NH3 data, so that needed to be smooth, as well as the spatial resolution of NH3 is intrinsically higher than that of the N2H+, so that needed to be smooth as well. So they were both smooth to a common beam size of 8 arc seconds and with a resolution of 0.07 kilometers per second. A little bit of a spoiler, but after I fitted these smooth cubes, which took a lot longer than it should have, I realized that the NH3 data and the N2H+ data weren't on the same grid. So I couldn't accurately compare their pixels. So I had to regrid the data, and I used PySpecKit to do that. But now let's move on to the actual fitting. To do the fitting, I used PySpecKit. I have a love-hate relationship with PySpecKit. At first, it's a very powerful tool, but I will say that it's where a lot of my issues came from this project. At first, I was fitting the N2H plus data and it was smooth sailing. I was so happy. I found all my parameters. I used the N2H plus V tau model and it ran for about 2.5 hours. The Q came out. I was so pleased and I was so excited to move on to the NH3 data. When I got to the NH3 data, I used PySpec-Kit's cold ammonia model because the data that we had was 1-1 and 2-2 transition. In the core that we had this time around, it wasn't hot enough to show the 3-3 transition, so that's why we used the cold ammonia model. And when I wrote my script, I was really just chugging along, really happy to just get these plots out. And the second I hit run, the very first thing, a giant block of like errors. And I was so confused. I didn't know where it came from. It was a bunch of jargon. I was scouring documentation to see if anything was like this. Couldn't find anything. But right in the middle, it said units not convertible, gigahertz to kilometers per second. And I was very confused because the majority of the time I've been working in velocity axis. So I had no idea where this gigahertz was even coming from. So I sent off this error to Annika. I was like, can you please help me with this? I have no idea what's going on. And she looked at it and she messaged me back. I have no idea what's going on. So we spent a couple weeks trying to replicate the error and see if we can fix it, but eventually it was a lost cause. So she sent me some new data. Maybe we're thinking it was an issue with the original data. I smoothed that and she sent me back a fitting script that she had used in the past that worked. And it worked. I mean, I was pretty happy with it. I was getting my plots. I essentially forgot about the issue that I was having. So one day I was poking around on PySpec-Kit's documentation and I found in the frequently asked questions, the only question was, what is this error? Oh my God. Turns out that I had forgot to set the reference axis, which I went through all 5 stages of grief in that moment because I had done that in the last fitting script. But I just forgot to carry it over. So I was kicking myself a little bit, but I did end up transitioning it to the new script. And I ran it. I was like, this is going to be it. There was another error. So I had already gotten Annika's script to work, and I waved goodbye to my script child and was like, okay, we'll move on from me. But yeah, that is a big issue that I ran into. So when it finally ended up working, I ran the script on one core and it took about 18 hours. And that was a little disheartening. And then when the regridding error happened, I didn't want to sit there for another 18 hours. So I upped the core up to about 8 cores and it took about 3.5 hours. And I was so happy. All my fits were presentable, looked at them in DS9, everything looked good. Came time to plot them. So I used ApplePie to do this, and I really did enjoy using ApplePie. It was my first time learning how to use it. And it is very astronomer friendly. I was very, very excited to learn how to use it. The only issue that I ran into is that it's not the most radio astronomer friendly. I found that when I was trying to plot my fitted cubes, it didn't really like to recenter. It took me so long to figure out what the error was. It was saying that there was no WSC axes, and I had no idea why. Turns out that the workaround that we had was to squeeze the axes so that there was no residual leftovers from when I ran the fit, and to separate each frame so that they were individual and I could just plot them one by one, and in that way they would recenter. This ended up working to my favor because in the future I ended up needing the individual data from each frame. So it was just a lot easier to call them individually and not have to worry about slicing the cube. So that's my little detour. But now the part you've all been waiting for, the actual maps. So this fit, the N2H plus fit, gave me 8 frames. It was the excitation temperature, optical thickness, line of sight velocity, and line widths, and their respective errors. The ones I really cared to look at were the excitation temperatures, line of sight velocity, and sigma maps. These were all within reason. I mean, when you look at these temperatures, they're to be expected. This axis is in Kelvin. This is in kilometers per second, as you can tell, a little bit faster on the outskirts and slower in the middle. And here also in kilometers per second. And as you can see, there is a density of wider lines in the center and narrower on the edges. Don't worry about remembering this map. This is the one we're going to care about in the future, but you'll see it again. So don't worry about remembering it. So those are the N2H plus maps. And then the NH3 maps are here. This fit gave me 12 frames. So the kinetic temperature, excitation temperature, column density, line of sight velocity, dispersion velocity, and the orthopara ratio and their respective errors. So once again, kinetic temperature within the core, reasonable temperatures, line of sight density, reasonable as well, a little bit more dense in the center, a little bit more diffuse as you go out. This kind of models the same thing as we saw in the last frame, a little bit faster on the edges and slower towards the center. And then same general values for the line widths, but a little bit narrower than the other. So to give you some confidence in my fits, here are the hyperfine model comparisons. So here I have in the black is the data, the red line is the model, and this gray line here is a signal to noise ratio. So as you can see, the black line here matches up pretty well with the model. So we're pretty confident in that. And then the signal to noise ratio doesn't look like it interferes too much with the data, which is very nice. As you can see here, the spectrum from A and C both come from, you can see right here. So moving on, here are the two line width maps side by side. So ion on the left, neutral on the right, and this is where I have a lot of information for you guys. But the spectral lines can broaden because energy levels aren't infinitely sharp. So molecules move and the temperature of gas can affect the random motions of these molecules, which causes thermal broadening of the spectral line. Random turbulent motion also causes line broadening, which is the non-thermal component. So using the kinetic temperature that I had mapped earlier, I was able to remove the thermal component from the fitted, which you will be seeing soon. But yes, this is just a way to tell by eye that it appears that the N2H plus has slightly more wider line widths than that of N2H plus. It's a little bit more concentrated in the center, or NH3. So what you've all been waiting for, the piece de resistance, the sonic Mach number comparisons, the same one from the plot that I had shown earlier. As you can see here, the blue is the ion, the red is the neutral, and we can tentatively say that the ion has a little bit more wider line widths than that of the neutral. Now, there are things to keep in mind. I haven't calculated the errors quite yet. So I had the code infrastructure for it, but I wanted to make sure that I was running it on the right data so that I didn't give you guys incorrect numbers. And as you can see here, the structure of this line is a lot broader than that of the neutral. So we were very confused and concerned as to why this is. And one hypothesis is that there could be a second velocity component. So here I have overlaid the unsmoothed data versus the raw data. So as I mentioned earlier, I had to smooth the N2H plus data to get it to match up with the NH3. And we suspect that that smoothing kind of glossed over some of the features from the raw data. So as you can see here, marginally, tentatively, there is a little bit of a dip in this hyperfine peak that's in the red, and then the black is what was smoothed over, the smooth data. So in the future, we do plan on trying to determine if there is in fact two velocity components. And if there is, then we would want to compare them to the neutral earlier to get more definitive answers. So that's my presentation. Any questions?
Thank you, Catalina, for a wonderful talk. We'll open it up to questions in the audience. So if we have any questions for those on Zoom, if you have a question, please unmute yourself and ask out loud. But we'll start with a question in the room. Go ahead.
Yeah, are these clouds known to have strong magnetic fields? So I wonder if that could affect ions. as opposed to
Yeah, so that
maybe
is one of the strong theories as to why this is actually happening. So they believe that it is possible that the magnetic field could be oscillating into the core as opposed to just being a static presence that could affect the ions. Emma?
Yeah, so to piggyback off of that, so you're saying in the beginning that previously it was found that one, I can't remember, I think it's the N2H plus had broader line widths.
Narrow.
Narrower, okay, and the other one is broader. So what type of objects does that have? Is it all molecular clouds or, I'm a
So-
galaxies person, so.
I'm not sure if it is all molecular clouds, but we've been working on mainly dense objects. I don't know, Monica, if you have anything else to add.
Typically, I mean, what you have is the line width size relationship, which kind of tells you that with decreasing, the deeper you go into the core, the line width of your line is getting narrower. So if you have a molecule that has tracing technically denser material, you're expecting it to have a narrower line width. And then from that theory, if you look at the critical densities or densities for the two molecules, N2H plus is the one that has the higher density. So you would expect it to trace the more inner parts and have the other way around, trace the more inner parts and have the narrower line widths, while we see that it has the wider line widths in some of the cores. So theory wise, you would assume that you see this in other cores, like when people observe this, they see that it is narrower, but we find now cores where it's the opposite, what you're not expecting. And then one of the hypotheses that goes with the magnetic field is that for B5 at least, we assume that it is coupled to the magnetic field, like the ions are coupled to the magnetic field and it's oscillating. So it moves into the core further, and then it widens the lines for moves the ion. It's more than it moves the neutral. By tracing more or less.
So some questions, I'll go with Jay first.
Yeah, could you show the slide showing the two different species of the line widths? Oh, no, back again, the actual maps. I mean, there are some regions where there's a factor of 2 difference in the line width. I'm thinking right sort of the lower left. It really does appear that it could almost even be different objects.
That's why we did the integrated intensity maps at the beginning, just to kind of show that we were in fact looking at the same thing.
I'm not suggesting that they are different options. It's just that they really do seem to be tracing different things.
Yeah. Jay?
Yeah, so
We'll go for
related to Jay's question is mine. Go to the velocity images. Those two things, this velocity structure that's different to as well. That's the line width.
Oh,
Keep going.
yes, sorry. Yes.
Okay, so that's, so the third panel to the right,
Mhm,
that's velocity for ammonia,
mhm.
and that's velocity, and they're very, very different.
Mhm.
And my thought is that the velocity, any change in velocity across a surface, like across an object, will also corrupt the line widths as well. And because the velocity structure is different, might be influencing what the actual line widths are. You're measuring a line width, but the line width is contaminated by the actual line width and the fact that across each pixel, the velocity of the object is changing.
Mhm.
So one thing, I don't know if anyone ever tried this, but if you take the two-dimensional derivative of the velocity map, that will tell you the point-by-point contribution of the velocity gradients in the line width of the measured line widths. And because that derivative is different between the two, they get different contamination in the velocity maps and the line width maps, and then maybe the comparison will be less obscure.
Definitely try that. Jen?
Is there any star formation happening in this cloud?
Yeah, so it's not in this cloud in particular. It's just the prestellar core itself. So it's on the verge of becoming.
So this is prestellar, it's on the verge of forming.
Is this excitation temperature map Are the units right there? Because it looks like it's 120 Kelvin in the middle.
I saw the same now. I'm curious about
That
this. I
seems-
did
that
not
seems
realize
really
this
hard.
before. It seems very, very hot for excitation temperature. I have to look into
How
this.
can you have
I've put
no
a
star
note.
formation?
Yeah, I put a note on this. So I looked at the more specific at the kinetic temperature with the 10 Kelvin was more to what I was expecting. I recently just saw this now. I'm sorry, that's totally on me. I missed that. Otherwise, I would have investigated that before that.
Yeah. That would suggest to me star formation. Of course, if there's star formation in the center of the cloud, then all bets are off because the stars, the feedback from the star
Yeah,
can have
that's-
turbulence.
The fun thing of learning apple pie for the first time is that you learn that the units to constrain the color bar is a lot different than that of DS9. So I spent a lot of my time going back and forth between the two. So there could be user error in there.
It seems-
Do we have any questions on Zoom? If you have a question on Zoom, go ahead and unmute yourself to ask it. If not, I will open it up to the room for final questions. All right, Evan.
What is the sonic Mach number?
So sonic Mach number is just a way that we compare the non-thermal velocity line widths. So if you look at the equation, I should have put it up there afterthought, but the equation is just the non-thermal line widths divided by the speed sound. So it's just a way to kind of visualize.
All right, well then, with that, if you have any further questions on Zoom, if you could unmute yourself. Sorry, we can't see the chat currently, so. Going once, going twice. Sold, all right, thank you, Catalina. Catalina, and I'm sure she'd be happy to answer them. So thank you all for coming, and thank you, Catalina, for closing out our summer talk series.
Oh my God.
I've seen that for you.
I probably forgot like half the stuff.
Huh?